When we open our eyes each morning, we step into a world that feels obvious. We move forward and backward, we step left and right, and we rise or sit down, up and down. These three directions of space are so ingrained in our lives that we rarely stop to question them. They seem complete. Everything we do, from walking across a room to driving across continents, unfolds within these three dimensions. Yet as natural as they feel, their simplicity hides the extraordinary fact that they are not the whole story. Physics teaches us that reality contains more than the space we see and feel. The idea of dimensions is as old as geometry itself. When ancient thinkers like Euclid described points, lines, and planes, they laid the foundation for how we imagine space. A point has no length, width, or height. A line has one measure, a plane has two, and a solid has three. This framework became the language of mathematics, art, and architecture. For more than 2,000 years, the three-dimensional view of space seemed final. The human brain evolved to perceive it, and our senses are tuned to it. But nature does not care what feels natural to us. It follows its own laws. In the early 20th century, Albert Einstein shattered the comfortable boundary between space and time. Before him, time was treated as something separate. It ticked away in the background, steady and universal, while space provided the stage on which events occurred. Einstein's theory of relativity revealed that this separation was an illusion. Time is not an independent river. Instead, it is woven with the three dimensions of space into a single fabric called space-time. This union was not a poetic metaphor, but a precise scientific statement. When we measure distances across the universe, or when we calculate how planets move around the sun, we must account for both space and time together. A light beam traveling across empty space does not just cover kilometers, it also covers seconds. The path it traces exists in 4 dimensions, not 3. This insight solved puzzles that Newton's mechanics could not. It explained why the orbit of Mercury shifted slightly each century, and why gravity seemed to act instantly at a distance. Gravity, in Einstein's picture, was not a mysterious pull. It was the bending of space-time itself. Imagine a heavy ball placed on a stretched sheet. The sheet curves, and a marble rolling nearby spirals inward. This is the image often used to explain Einstein's discovery. The ball represents a star, or planet. The sheet represents space-time, and the marble represents another body. In reality, space-time has 4 dimensions, so the true picture is more abstract, but the analogy captures the core idea. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. This way of thinking about the cosmos transformed physics. It explained black holes, regions where space-time folds so steeply that nothing, not even light, can escape. It predicted the expansion of the universe itself, a fact later confirmed by observations of distant galaxies rushing away from us. It even allowed physicists to describe gravitational waves, ripples in space-time, that have since been detected directly by observatories on Earth. Yet despite its triumphs, 4-dimensional space-time carries limitations. Einstein's general relativity explains the force of gravity with elegance, but it does not describe the other forces of nature. Electromagnetism, the force that makes light travel and atoms bind, still requires the framework of quantum theory. The nuclear forces that hold protons and neutrons together are described by a separate quantum field theory, known as the Standard Model. These 2 great pillars of physics, general relativity and quantum theory, work beautifully in their own domains, but they clash when applied together. The equations break down at the smallest scales and at the highest energies, such as inside black holes or during the birth of the universe. This failure has led physicists to ask whether our 4-dimensional view is only part of reality. Could the deep incompatibility between gravity and quantum mechanics hint at something missing? What if space-time itself is not limited to 3 dimensions of space and 1 of time? What if there are hidden directions curled beyond our senses, invisible yet fundamental? This question is not idle speculation. The search for unification, the dream of a single framework that explains all forces, drives modern physics. When we look at the known forces, 3 of them fit neatly into the standard model through the mathematics of quantum fields. Gravity resists inclusion. It is far weaker than the others, by an astonishing factor of 10 to the power of 38, compared to electromagnetism. Why such a vast gap exists is one of the most troubling mysteries in science. Some theorists suspect that the answer lies in dimensions beyond the 4 we experience. Our everyday world provides no clue of these possible hidden directions. We cannot turn our head and look into a 5th dimension, but mathematics allows us to describe them, and experiments can be designed to test their effects. To understand how scientists came to seriously consider extra dimensions, we must trace a path through both mathematics and physics. The story begins not with Einstein, but with the language of geometry itself, which showed long ago that more than 3 dimensions are perfectly possible to imagine. And so the journey begins, with the simple act of asking a profound question. If space and time, as we know them, are not enough, what deeper structure might reality hold? The idea of extra dimensions may sound strange, but the concept of dimensions themselves deserves closer thought. A dimension is simply a way to measure change. When we walk down a street, we measure how far we have gone in length. When we cross a field from one side to another, we measure width. When we climb a mountain, we measure height. These 3 measures are independent of one another, and they define the 3-dimensional space of our lives. Time is added as the 4th, marking change that unfolds and never repeats. It flows in one direction, giving events an order and anchoring memory and cause. Without time, the universe would be frozen, a silent sculpture with no motion or life. It is tempting to believe that these 4 are all reality can offer, but mathematics began to challenge that belief long before physics had reason to. In the 19th century, the German mathematician Bernhard Riemann gave a lecture that would change the very way we imagine space. He showed that geometry does not have to be flat, like the grid of a notebook page. Instead, space itself can be curved, like the surface of a sphere. He went further, explaining that such curvature can exist not just in 2 or 3 dimensions, but in any number. His equations made perfect sense even if one imagined 4, 5, or more dimensions. This was not science fiction. It was rigorous mathematics, a language that allowed reality to be described in ways the senses cannot directly picture. For most people, visualizing 4 spatial dimensions is impossible. Our brains evolve for survival in 3-dimensional environments, not for abstract spaces. Yet analogies can help. Imagine a 2-dimensional creature living on a flat sheet of paper. This being knows only length and width. Height is unimaginable. Now picture a sphere passing through its world. At first the creature sees a dot appear. Then the dot grows into a circle, expanding until it reaches a maximum size, and then shrinking again before vanishing. To the 2-dimensional being, something mysterious has happened. But from our perspective, we know the full truth. A 3-dimensional sphere has passed through a 2-dimensional plane. In the same way, our 3-dimensional experience might be just a shadow of a larger structure. What we perceive as matter and energy could be the intersection of higher dimensional processes with our limited view. This possibility is not merely philosophical. It is one of the guiding ideas in the attempt to reconcile physics at its deepest levels. If forces like gravity spread through extra dimensions, it might explain why gravity seems so weak compared to electromagnetism or nuclear forces. Einstein's relativity already hinted at the power of reimagining dimensions. Time had always been separate from space, but by merging them into a 4-dimensional space-time, Einstein resolved contradictions that had troubled physics for decades. If adding a single new dimension could bring such clarity, why not explore what might happen if more are added? In fact, only a few years after Einstein presented his theory, physicists began to wonder if reality might require a 5th dimension. The stage was set by the union of mathematics and physics. On one side, geometry showed that higher dimensions are perfectly consistent, even if we cannot picture them. On the other, relativity showed that treating time as a dimension yields profound physical insight. The next step was to ask whether dimensions beyond the familiar 4 could play a role in uniting the forces of nature. Could the laws of electricity, magnetism, and gravity be different facets of a single underlying geometry. The search for such unity is not simply an abstract pursuit. History has shown that unification brings breakthroughs. Electricity and magnetism were once thought to be separate. In the 19th century, James Clerk Maxwell demonstrated that they are two sides of the same coin, described by a single set of equations. His discovery revealed that light itself is an electromagnetic wave. If electricity and magnetism could be unified, perhaps gravity and electromagnetism could be joined as well. Such a step might reveal hidden dimensions as essential to reality. But before physics made this leap, humanity had to adjust to an even stranger truth. The universe was not fixed and eternal, as many once believed. It was dynamic, with space and time themselves capable of bending, stretching, and warping. This realization did not come easily, and even today, it challenges intuition. When we look up at the night sky, it feels as if the stars are set upon a vast, still backdrop. Yet that backdrop is flexible, like an invisible fabric. It can ripple with gravitational waves. It can expand, carrying galaxies apart. It can collapse, forming black holes. By the time these discoveries settled into scientific consensus, the seeds for exploring more than 4 dimensions had already been planted. The next stage would require daring imagination. A physicist named Theodore Kaluza would soon take the bold step of suggesting that Einstein's 4-dimensional spacetime might not be enough. Perhaps there was a hidden 5th dimension, too small for us to notice, but crucial for explaining the forces of nature. The path from the everyday world of length, width, height, and time to the possibility of hidden dimensions is a path of expanding vision. It asks us to admit that what seems complete to our senses may be just a fraction of reality. Just as ancient navigators once thought the horizon was the edge of the world, we might be standing at the shore of a far deeper ocean of dimensions. The leap from 4 to 5 was only the beginning of a journey that still continues today. The notion of hidden dimensions forces us to ask a simple but unsettling question. Why do we experience only 3 spatial directions and 1 temporal flow? If mathematics allows more, why does nature seem to restrict us? The answer may lie in the difference between what exists and what can be observed. Our senses are limited instruments. They evolved to help our ancestors find food, escape predators, and navigate landscapes. There was no evolutionary advantage in perceiving higher dimensional structures. Even today, with powerful telescopes and particle colliders, we can only measure effects within the slice of reality that interacts with our instruments. It may be that other dimensions exist, but they are compact, hidden, or expressed only through subtle, physical consequences. Einstein's equations themselves hinted at this possibility. His description of space-time geometry does not forbid extra dimensions. It simply does not require them for the phenomena we have measured so far. When physicists extend the mathematics, adding a 5th coordinate does not break relativity. Instead, it offers room for new patterns to emerge. The question is not whether the equations allow higher dimensions, but whether the universe itself uses them. A useful way to think about this is through the idea of compactification. Imagine a garden hose stretched across the ground. From a distance, it looks like a simple line, one-dimensional. But as you draw closer, you notice the hose has thickness, wrapping around in a circular cross-section. For an ant crawling along the hose, there are 2 ways to move: forward along its length or around its circumference. What looked like 1 dimension from afar actually contains 2. In a similar way, our universe could hold dimensions that are curled up so tightly we cannot perceive them at human scales. They would be as real as length, width, and height, but hidden within the fabric of space-time. This line of thought grew more persuasive as physics advanced. In the early 20th century, quantum mechanics revealed that the subatomic world behaves in ways utterly unlike the macroscopic. Electrons orbiting an atom are not tiny planets circling a miniature sundae. They exist in probability clouds, spread across regions of space until measured. Light behaves both as a particle and as a wave. These discoveries shattered the illusion that human intuition is a reliable guide to nature. If particles can tunnel through barriers, and if time can dilate for objects moving near the speed of light, then hidden dimensions no longer seem absurd. They become a natural extension of the lesson that the universe is stranger than appearances suggest. It is important to note that hidden dimensions are not proposed for convenience or aesthetic beauty alone. They are motivated by genuine gaps in our understanding. Gravity remains the great outlier among the forces, while electromagnetism, the strong nuclear force, and the weak nuclear force can be described in one framework. Gravity stubbornly resists. Its incredible weakness compared to the other forces remains unexplained. The possibility that it leaks into extra dimensions offers one potential answer. The drive to unify physics has always been about more than equations. It is about finding harmony in the laws of nature. When Maxwell united electricity and magnetism, he revealed that light itself is part of the same phenomenon. When Einstein united space and time, he reshaped our view of the cosmos. The suggestion that adding a fifth dimension might unite gravity with electromagnetism followed in this tradition. Even if our senses cannot grasp such a dimension, the logic of science invites us to explore it. This exploration will carry us into bold territory. It will show how mathematics provided a blueprint long before experiments could confirm or deny it. It will lead us through the work of Kaluza and Klein, who first dared to extend relativity into higher dimensions. It will then carry us into the strange but rigorous world of string theory, where the very fabric of matter demands extra dimensions to exist. Along the way, we will see how modern physics has designed experiments to search for evidence, from probing gravity at microscopic distances to listening for subtle patterns in the cosmic microwave background. Chapter 1 closes with a simple but profound realization. The 4 dimensions we know are not guaranteed to be the limit of reality. They may be only the visible shoreline of a much larger continent of existence. The history of science warns us against assuming that what we see is all there is. Beyond the horizon of human perception may lie structures richer and stranger than our imagination, waiting for the right insight or experiment to reveal them. And so we step forward into Chapter 2, where the language of higher dimensions is no longer philosophical speculation, but a rigorous branch of mathematics, ready to show us that our universe may hold more than meets the eye. When we think of mathematics, most of us picture numbers on a page, or simple shapes like triangles and circles. But mathematics is not only a tool for counting or drawing, it is a language that allows us to describe patterns and structures far beyond what our senses can perceive. Long before physics demanded extra dimensions, mathematics had already shown they were possible. This chapter tells the story of how higher dimensions emerged, not from science fiction, but from precise reasoning, carried forward by some of the greatest minds in history. The origins lie in geometry, a subject that dates back to ancient civilizations. Euclid's Elements, written over 2,000 years ago in Greece, set down rules for points, lines, planes, and solids. These rules described a universe of 3 dimensions that matched human experience. Builders used them to construct temples, astronomers used them to map the stars, artists used them to capture perspective in paintings. Geometry seemed complete, but as centuries passed, cracks began to appear. One of the biggest questions was the nature of parallel lines. Euclid's geometry assumed that if 2 lines were parallel, they would never meet, no matter how far they were extended. For generations, mathematicians tried to prove this assumption from other principles, but none succeeded. Finally, in the 19th century, several thinkers dared to ask, what if parallel lines can meet? This question led to new kinds of geometry, where space itself could be curved. The German mathematician Bernhard Riemann gave a lecture in 1854 that marked a turning point. He showed that geometry could describe spaces of any number of dimensions, not just 2 or 3. More importantly, these spaces could have curvature. A flat sheet and the surface of a sphere are both 2-dimensional, but one is flat and the other is curved. Riemann extended this idea to spaces that could never be drawn on paper. He provided equations that made sense even in 4, 5, or 100 dimensions. Mathematics no longer depended on human intuition. It had become a tool for exploring the unseen. To grasp the leap Riemann made, it helps to think again about analogies. Imagine a cube. It is 3-dimensional, with 12 edges. 6 faces, and 8 corners. Now imagine extending this logic one step further. What happens if we add a 4th spatial dimension? The result is a hypercube, also called a tesseract. It has 16 corners, 32 edges, 24 square faces, and 8 cubic cells. We cannot visualize it fully, but we can project it into 3 dimensions, just as a cube can be projected onto a sheet of paper. Artists and scientists have drawn these projections, creating shapes that look like cubes, nested inside one another, connected by stretched edges. They are shadows of a higher dimensional object, just as a 2-dimensional drawing of a cube is a shadow of the real thing. These analogies show that higher dimensions are not fantasies. They are logical extensions of geometry. A mathematician can describe the properties of a 10-dimensional object with as much rigor as a carpenter can describe the angles of a chair. The difference is that we can never build the 10-dimensional object in our physical world, but the equations remain perfectly valid. By the late 19th century, mathematicians like Riemann, and later David Hilbert, had laid out a framework where higher dimensions were as natural as 3. The challenge was not whether they could exist in theory, but whether they had anything to do with the physical universe. At the time, physics had no need for them. Newton's laws worked well enough to explain motion. Maxwell's equations united electricity and magnetism in 4-dimensional spacetime. The idea of extra dimensions seemed like pure abstraction, a playground for mathematicians but irrelevant to nature. Yet mathematics has often run ahead of physics, preparing the ground for discoveries not yet made. Calculus, invented in the 17th century, found its greatest use centuries later in describing motion and change. Non-Euclidean geometry, once considered useless, became essential to Einstein's theory of relativity. The language of higher dimensions would eventually serve a similar role, providing the framework needed when physics reached its limits in 4-dimensional spacetime. This connection between mathematics and physics is not accidental. The universe follows laws that can be expressed in numbers and patterns. The ability of abstract mathematics to describe the natural world so precisely remains one of the greatest mysteries of science. The equations Riemann wrote in the 19th century seemed like pure imagination, but they became the foundation for Einstein's curved spacetime in the 20th. And when Einstein's equations were later extended by others to include a 5th dimension, the groundwork was already laid. The lesson is that mathematics is more than a human invention. It is a discovery of the deep structures that underlie reality. We may never directly see a 10-dimensional object, but the equations describing it can reveal truths about the universe we do live in. Just as a map can represent a landscape without duplicating it, mathematics can represent higher dimensional structures that our senses cannot grasp. By the dawn of the 20th century, the idea of higher dimensions had matured mathematically. It was no longer a curiosity, but a robust field. When physicists began searching for deeper unity between forces, they found a ready-made toolkit waiting for them. The leap from mathematics to physics was about to be made, and with it, the possibility that hidden dimensions might not just be logical, but real. And so, the story moves forward to a bold proposal in 1921, when Theodore Kaluza took Einstein's equations and asked, what if spacetime had one more dimension? The leap from 3 dimensions to 4 was already profound, but the step into 5 or more begins to stretch human imagination to its limit. Still, mathematics gives us the tools to explore such spaces without the need for physical intuition. To see why this matters for physics, we must first understand how higher dimensions behave and why they are not merely abstract curiosities, but consistent systems with their own rules. Think again about the hypercube, or tesseract. It exists in 4 spatial dimensions, though we can only glimpse its shadow in 3. When we draw it on paper, we see what looks like a cube inside another cube, joined at the corners. This is no different from how a cube looks like a square within a square when drawn on a flat page. Each step up in dimension involves extending an existing object in a new direction. In 2 dimensions, we move a line sideways to get a square. In 3 dimensions, we move a square upward to get a cube. In 4 dimensions, we move a cube along an axis perpendicular to all 3 familiar directions to get a hypercube. The pattern continues endlessly. Even if our minds cannot picture it directly, mathematicians use symbols and coordinates to describe these structures precisely. In 3 dimensions, we specify a point by giving 3 numbers, such as length, width, and height. In 4, we add a 4th coordinate. In 10, we would need 10 numbers. Nothing in the mathematics breaks when we go beyond 3. The rules of geometry and algebra continue to work. That consistency is what makes higher dimensions more than daydreams. They are logical extensions of the system that already describes the world we live in. One might ask, if higher dimensions are so natural mathematically, why do we not encounter them physically? The answer may be that we do encounter them, but only indirectly, through the effects they have on what we can measure. For example, when Einstein used Riemann's mathematics to describe gravity as the curvature of space-time, he showed that a massive body like the Sun does not pull planets with an invisible force. Instead, it bends the geometry around it, and planets follow the curves of that geometry. The mathematics of curved space turned out to be a more accurate description of reality than Newton's simpler laws. In this way, higher dimensional mathematics prepared the ground for new physics. The moment physicists saw that 4-dimensional spacetime explained gravity, it became reasonable to ask whether adding more dimensions might explain even more. Could electromagnetism, the force behind light and electricity, also be a manifestation of geometry in a higher dimensional space? Could the nuclear forces, which seemed so mysterious in the early 20th century, eventually be drawn into the same picture? The search for such unification was not motivated by speculation but by the striking success of earlier unifications. When light turned out to be part of the same framework as electricity and magnetism, the promise of discovering a larger unity became irresistible. Visual analogies continue to play an important role in helping scientists and the public grasp these ideas. Consider again the 2-dimensional being living on a sheet of paper. For that creature, the 3rd dimension is inconceivable. Yet, we, standing above the paper, can reach into its world, lift it up, or even fold its plane. From the point of view of the flat being, such actions would seem miraculous, but to us, they are simple consequences of existing in a higher dimension. If our universe has hidden directions, the effects of those directions might appear miraculous as well, until we recognize them as part of a larger geometry. Mathematicians in the 19th century explored these possibilities with growing confidence. They studied how lines, planes, and solids could extend into spaces with any number of dimensions. They developed formulas to calculate volumes, areas, and angles in these abstract realms. What they discovered was that higher dimensions are not just consistent but often reveal surprising patterns. For example, as the number of dimensions increases, the geometry of spheres and cubes behaves in unexpected ways. The volume of a sphere relative to the cube that contains it shrinks as dimensions rise, an effect that challenges intuition but follows logically from the mathematics. This growing body of knowledge remained, for the most part, a mathematical playground until physics caught up. Yet even before Einstein, there were hints that geometry might have deeper physical meaning. Maxwell's equations for electromagnetism, written in the mid-19th century, already hinted at a unity of forces. The discovery of radio waves by Heinrich Hertz showed that these equations described real physical phenomena. The success of Maxwell's unification made physicists wonder if something similar might apply to other forces. Mathematics offered the possibility that geometry in higher dimensions could be the key. By the turn of the 20th century, the stage was set. Mathematicians had built a vast toolkit for describing curved spaces of many dimensions. Physicists had discovered the unity of electricity and magnetism, and Einstein had shown that gravity itself was geometry in 4-dimensional spacetime. The question hanging in the air was clear. If 4 dimensions explain gravity, could 5 explain more? The answer would soon come in the form of Kaluza's bold idea, which extended Einstein's relativity into a 5th dimension. But before that leap could be made, physics had to accept a truth that mathematics had revealed decades earlier. higher dimensions are not impossible. They are not even unusual. They are part of the logical structure of geometry itself, waiting for nature to reveal whether it uses them. The moment when physics first embraced this possibility marks a turning point. What began as abstract reasoning about parallel lines and curved spaces became a gateway to some of the most daring theories ever proposed. The bridge between mathematics and reality was about to be crossed, and with it, the concept of hidden dimensions would enter the heart of physics. The bridge between mathematics and physics is one of the most mysterious connections in human thought. Abstract symbols written by mathematicians who had no concern for physical reality later became the very language that explained the universe. This was the case with calculus, which Isaac Newton and Gottfried Wilhelm Leibniz developed to study motion, but which later became indispensable for every branch of science. It was the case with non-Euclidean geometry, which seemed like a mental game until it provided the foundation for Einstein's curved spacetime. And it would soon be the case with higher dimensions, which mathematicians had studied for their own sake, but which physicists would use to attempt the deepest unification of forces. One of the ways mathematicians tested the idea of higher dimensions was through projection. Just as a three-dimensional object casts a two-dimensional shadow, a four-dimensional object can cast a three-dimensional shadow. These shadows can be drawn and studied, revealing patterns that hint at the structure of the original. The tesseract, the four-dimensional cube, is one example. Another is the four-dimensional sphere or hypersphere. While we cannot hold a hypersphere in our hands, we can calculate its volume, surface area, and properties with precision. These exercises showed that higher dimensions were not fanciful inventions. They were consistent realities within mathematics. The fact that these constructions were so orderly led some to suspect they might reflect a deeper order in nature itself. If geometry is the language of the universe, then perhaps the universe speaks in more dimensions than we perceive. Einstein himself was aware of this possibility. In his theory of general relativity, he used Riemann's geometry to describe how matter and energy curve spacetime. Without Riemann's mathematics, the theory would not have been possible. This showed beyond doubt that abstract mathematical ideas could become physical truths. It opened the door for others to wonder whether additional dimensions, already well understood mathematically, might also be real. Another key development in the 19th century was the study of symmetry. Symmetry in mathematics is more than aesthetic balance. It is a property that reveals deep conservation laws in physics. For example, when we think of mathematics, most of us picture numbers on a page, or simple shapes like triangles and circles. But mathematics is not only a tool for counting or drawing, it is a language that allows us to describe patterns and structures far beyond what our senses can perceive. Long before physics demanded extra dimensions, mathematics had already shown they were possible. This chapter tells the story of how higher dimensions emerged, not from science fiction, but from precise reasoning, carried forward by some of the greatest minds in history. The origins lie in geometry, a subject that dates back to ancient civilizations. Euclid's Elements, written over 2,000 years ago in Greece, set down rules for points, lines, planes, and solids. These rules described a universe of three dimensions that matched human experience. Builders used them to construct temples, astronomers used them to map the stars, artists used them to capture perspective in paintings. Geometry seemed complete, but as centuries passed, cracks began to appear. One of the biggest questions was the nature of parallel lines. Euclid's geometry assumed that if two lines were parallel, they would never meet, no matter how far they were extended. For generations, mathematicians tried to prove this assumption from other principles, but none succeeded. Finally, in the 19th century, several thinkers dared to ask, what if parallel lines can meet? This question led to new kinds of geometry, where space itself could be curved. The German mathematician Bernhard Riemann gave a lecture in 1854 that marked a turning point. He showed that geometry could describe spaces of any number of dimensions, not just two or three. More importantly, these spaces could have curvature. A flat sheet and the surface of a sphere are both two-dimensional, but one is flat and the other is curved. Riemann extended this idea to spaces that could never be drawn on paper. He provided equations that made sense even in 4, 5, or 100 dimensions. Mathematics no longer depended on human intuition. It had become a tool for exploring the unseen. To grasp the leap Riemann made, it helps to think again about analogies. Imagine a cube. It is three-dimensional, with 12 edges, 6 faces, and 8 corners. Now imagine extending this logic one step further. What happens if we add a fourth spatial dimension? The result is a hypercube, also called a tesseract. It has 16 corners, 32 edges, 24 square faces, and 8 cubic cells. We cannot visualize it fully, but we can project it into 3 dimensions, just as a cube can be projected onto a sheet of paper. Artists and scientists have drawn these projections, creating shapes that look like cubes, nested inside one another, connected by stretched edges. They are shadows of a higher dimensional object, just as a 2-dimensional drawing of a cube is a shadow of the real thing. These analogies show that higher dimensions are not fantasies. They are logical extensions of geometry. A mathematician can describe the properties of a 10-dimensional object with as much rigor as a carpenter can describe the angles of a chair. The difference is that we can never build the 10-dimensional object in our physical world, but the equations remain perfectly valid. By the late 19th century, mathematicians like Riemann, in the early years of the 20th century, Einstein's theory of general relativity had already changed physics forever. By merging space and time into space-time, and by showing that gravity is not a force but the bending of geometry itself, Einstein revealed that reality is deeper and stranger than anyone had imagined. Yet even as relativity triumphed, it left physicists restless. Gravity was now understood as geometry, but electromagnetism remained separate. Maxwell's equations worked perfectly, but they seemed to sit apart from Einstein's elegant framework. Could there be a way to bring them together? Could gravity and electromagnetism, the two great forces known at the time, be unified within a single structure? Theodor Kaluza, a mathematician in Germany, dared to ask this question. In 1921, he sent a letter to Einstein suggesting an audacious idea. What if space-time had not 4 but 5 dimensions? Kaluza extended Einstein's equations into this extra coordinate, and what he found was astonishing. The equations of general relativity in 5 dimensions did not only describe gravity, hidden within them were the equations of electromagnetism as well. In one stroke, Kaluza had combined 2 pillars of physics into a single framework. The idea was radical, but the mathematics was clear. Just as Einstein had shown that gravity could be explained by the curvature of 4-dimensional space-time, Kaluza showed that electromagnetism could be understood as geometry in a higher dimension. To an observer limited to 4 dimensions, electromagnetism would appear as a separate force. But from the higher dimensional perspective, it was simply part of the geometry of the universe. This proposal electrified the small circle of physicists who could grasp its implications. It was the first serious attempt to use hidden dimensions, not as a curiosity, but as a physical necessity. If true, it meant that nature itself might be more unified than it appears. It also meant that what we experience as distinct forces might just be different aspects of geometry in a higher dimensional space. Yet the idea faced a major challenge. If there is a 5th dimension, why do we not see it? We can move forward and backward, left and right, up and down. We can measure time, but no experiment shows a 5th direction of space. Kaluza had no answer, and his theory, though elegant, could not be tested directly. Einstein himself was intrigued but cautious. He supported the idea, but did not pursue it with urgency, aware that it lacked empirical grounding. The missing piece came from Oskar Klein, a Swedish physicist who worked on the problem in the 1920s. Klein suggested that the 5th dimension might be real but compactified, curled up into a tiny circle far too small for us to notice. He compared it to walking on a garden hose. From far away, the hose looks like a 1-dimensional line. Only when you come close do you see that it also has a circular dimension. In the same way, space-time could have an extra direction, but if it is curled up at a scale smaller than an atom, it would escape detection. This idea of compactification gave the Kaluza-Klein theory new strength. It explained why we cannot move in the fifth dimension and why it appears hidden. More importantly, it provided a way for mathematics to produce not only gravity and electromagnetism, but also the quantization of electric charge. Klein showed that the allowed motions in the compact dimension would naturally lead to the discrete charges observed in nature. This was a remarkable success, a glimpse of how extra dimensions might explain features of the physical world that had previously been mysterious. For a time, the Kaluza-Klein idea seemed to point the way to a deeper unity, but as physics advanced, new forces were discovered, and the challenge of unification grew. The strong and weak nuclear forces, unknown in Kaluza's day, demanded inclusion in any complete theory. The standard model of particle physics emerged in the mid-20th century, describing three forces with extraordinary precision but leaving gravity out. The Kaluza-Klein framework, designed to unite only gravity and electromagnetism, was not enough. Still, the idea did not die. It lingered in the background, a reminder that higher dimensions could be more than abstractions. The mathematics was too elegant to ignore. And decades later, when string theory rose to prominence, physicists rediscovered compactification and higher dimensional geometry as central tools. The seeds planted by Kaluza and Klein blossomed into entire new branches of theoretical physics. The story of Kaluza-Klein theory shows the daring that drives science forward. It is one thing to extend known equations, but it is another to propose an entirely new dimension of reality. Kaluza and Klein did so with courage and rigor, laying the groundwork for modern theories that still seek to unify all forces. Though their model could not explain everything, it offered a vision of what unification might look like, and it demonstrated that higher dimensions could be taken seriously in physics. As this chapter ends, we can see the path stretching forward. Kaluza and Klein opened the door, but the real explosion of higher dimensional physics would come later, with string theory. There, the requirement of extra dimensions would not be an optional idea but an unavoidable necessity, and the compact spaces imagined by Klein would become the rich Calabi-Yau manifolds that shaped the geometry of strings. From this point, the search for hidden dimensions was no longer just an elegant possibility. It became a central demand of the mathematics itself. The universe, if described by strings instead of point particles, required more than 4 dimensions. And so the question sharpened. If mathematics demands extra dimensions, does nature agree? The answer lies in the next chapter, where the birth of string theory brings higher dimensions to the very heart of physics. Kaluza's suggestion of a 5th dimension was bold, but it was Klein's insight that gave the theory staying power. By imagining the extra dimension as curled up so tightly that it was invisible to our senses and instruments, Klein provided a mechanism for how such a dimension could exist without contradicting everyday experience. He calculated that the size of this compactified circle might be on the order of the Planck length, which is about 10 to the power of minus 35 meters. At such an unimaginably small scale, no experiment of the time could hope to detect it. This idea was not merely a convenient trick, it had profound consequences. In Klein's treatment, particles moving through the compactified dimension could only occupy certain discrete states, much like a guitar string that can vibrate only at specific frequencies. These allowed states corresponded naturally to the quantized electric charges observed in nature. In this way, the geometry of the hidden dimension explained a mystery that had long puzzled physicists. Electric charge was not an arbitrary feature of matter. It was a consequence of motion in a curled-up dimension. The beauty of this idea caught the imagination of theorists, but beauty alone is not enough in science. Without experimental evidence, the theory could not be confirmed. The instruments of the 1920s and 1930s were far too crude to test effects at the Planck scale. Even Einstein, who admired Kaluza's mathematics, regarded the proposal as intriguing but unproven. He corresponded with Kaluza and encouraged his work, but did not adopt it as part of his main research program. As decades passed, physics moved on. The quantum revolution reshaped the field, explaining atomic spectra, chemical bonds, and nuclear reactions. The Standard Model grew into a powerful framework that accounted for electromagnetism, the weak force, and the strong force. In this new landscape, the Kaluza-Klein idea looked outdated, uniting only gravity and electromagnetism, while leaving out the nuclear forces that dominated atomic physics. By the mid-20th century, few physicists gave it much attention. Yet the idea never disappeared completely. It lingered as a curiosity, resurfacing occasionally when theorists sought inspiration. In the 1960s and 70s, as string theory began to emerge, researchers noticed that its mathematics naturally produced extra dimensions. Suddenly, the logic of Kaluza and Klein returned, now supported by a richer framework. The curled-up circles of the old theory became compact spaces of extraordinary complexity, known as Calabi-Yau manifolds. The idea of hidden dimensions had been reborn. Looking back, it is striking how far ahead of their time Kaluza and Klein were. They proposed extra dimensions decades before physics had the tools to seriously consider them. Their vision showed that geometry could unify forces in ways no one had imagined. Even though their model could not explain everything, it demonstrated a path forward. It also planted a seed in the collective imagination of physicists, reminding them that nature might be structured in ways far beyond what our senses reveal. The Kaluza-Klein idea also foreshadowed a pattern in theoretical physics. Time and again, abstract mathematics has pointed the way toward physical truth. The equations do not always match experiment immediately, but they often lay dormant until technology or new ideas catch up. In this sense, Kaluza and Klein were part of a tradition stretching back to Riemann and forward to string theorists of the modern era. They trusted the language of geometry to reveal truths that human perception could not. Although experiments have yet to confirm extra dimensions, modern particle physics continues to test ideas inspired by Kaluza and Klein. Some models predict that at extremely high energies, such as those probed by particle accelerators, new effects might appear. Others suggest that gravity could deviate from its familiar inverse square law at very short distances if it spreads into hidden dimensions. These possibilities are direct descendants of the vision first outlined in 1921. In the end, the Kaluza-Klein theory is remembered less as a complete solution and more as a milestone. It showed that extra dimensions are not mere fantasy. They are mathematically consistent, and they can yield physical consequences that match real features of the world. Though the theory itself could not survive in its original form, it opened the door for future generations. It taught physicists to look beyond the limits of perception, to trust that geometry might hold the key to unification, and to accept that reality may be far richer than common sense suggests. As we close this part of the story, we can see how the idea of hidden dimensions evolved from pure mathematics to speculative physics. The journey from Riemann's abstract spaces to Kaluza's equations and Klein's compactification was the first real attempt to use higher dimensions to explain nature. It was a daring leap, and it left behind a legacy that continues to shape theoretical physics today. The next step would come from an entirely new direction, where the particles themselves were reimagined not as points but as vibrating strings. In that vision, extra dimensions would no longer be optional, they would be required. In the years following Kaluza and Klein, the physics community largely turned its attention elsewhere. Quantum mechanics was rewriting the rules of the microscopic world, and discoveries about the nucleus of the atom demanded urgent answers. The strange behavior of particles like electrons, protons, and neutrons pushed theorists into new territory. Questions about hidden dimensions seemed distant compared to the pressing need to understand how atoms worked, how stars shined, and how the new quantum rules could be reconciled with relativity. For a time, Kaluza and Klein's vision of a fifth dimension looked like a beautiful but isolated chapter in physics, admired but not actively pursued. Still, even as the field moved on, the idea remained quietly alive. Some physicists kept the theory in mind as an example of how mathematics could hint at deeper truths. Others revisited it now and then, looking for ways to adapt it to new discoveries. By the mid-20th century, with the Standard Model taking shape, the dream of unification once again became central. Physicists had succeeded in merging the weak nuclear force with electromagnetism into what became known as the electroweak theory. A triumph confirmed by experiment, yet gravity remained outside the framework, stubbornly resisting all attempts at inclusion. The Kaluza-Klein idea, with its vision of unification through higher dimensions, gained a second life as inspiration for new attempts. One of the most intriguing aspects of the theory was its treatment of geometry as physical reality. For centuries, geometry had been the study of shapes and spaces, an abstract branch of mathematics. But Einstein had shown that geometry could describe real physical phenomena. Kaluza and Klein pushed this further, suggesting that even the properties of charge could emerge from geometry in a higher dimension. In this sense, the Kaluza-Klein idea represented not just a scientific proposal but a philosophical shift. It implied that what we call forces might be nothing more than the shadows of geometry in spaces beyond our perception. As technology advanced, theorists began to ask what signatures of extra dimensions might be visible. Could particle accelerators ever reach energies high enough to reveal them? Could gravity experiments detect tiny deviations from Newton's inverse square law if gravity spread into more than 3 dimensions? In the late 20th and early 21st centuries, these questions became the focus of real experiments. While no evidence has yet been found, the possibility remains open. Each new search tightens the limits on what hidden dimensions could look like, guiding theorists toward more precise models. Kaluza and Klein also left behind a legacy in the way physicists think about compactification. Their idea of curling up a dimension into a tiny circle laid the groundwork for the far more intricate compact spaces used in string theory. In that later framework, extra dimensions are not merely circles, but complex geometries called Calabi-Yau manifolds, rich with structure. The seed planted by Klein's garden hose analogy grew into a vast branch of modern physics. Without their early work, the mathematical leap into 10 or 11 dimensions required by string theory would have been far more difficult to imagine. Looking back, it is easy to underestimate the courage required to propose an unseen dimension. At the time, there was no experimental hint, no pressing problem that demanded such a radical step. Kaluza trusted the mathematics, and Klein added the crucial physical insight. Together, they demonstrated that science could go beyond the limits of perception without leaving the ground of evidence and logic. Their theory may not have been confirmed, but it showed the direction in which unification might lie. It inspired generations of physicists to search for hidden structures, to imagine that the universe might hold more than the eye can see, and to believe that the key to unity might be found in geometry itself. As we close this chapter, we stand at a turning point. The Kaluza-Klein idea was not the final answer, but it was the first bold step into a new world. It showed that hidden dimensions could be more than imagination, that they could play a role in explaining the deepest mysteries of physics. The next stage of the journey would push these ideas even further. In the strange new theory of strings, extra dimensions would not simply be optional. They would be required for the very consistency of the mathematics. The leap from Kaluza's 5th dimension to the 10 dimensions of string theory would mark the beginning of a new era in theoretical physics, one in which hidden dimensions became not a choice, but a necessity. By the middle of the 20th century, physics had entered an age of astonishing discovery. The atomic nucleus had been split, revealing a zoo of particles that seemed to multiply with every new experiment. Protons and neutrons were no longer the smallest building blocks of matter. Beneath them, strange new particles appeared, each with its own properties, lifetimes, and interactions. To make sense of this growing complexity, theorists developed the Standard Model, a framework based on quantum field theory that successfully described 3 of the 4 known forces of nature: electromagnetism, the weak nuclear force, and the strong nuclear force. The Standard Model explained much, but one force remained outside its reach: gravity, so well described by Einstein's general relativity, resisted incorporation. The clash between relativity and quantum theory grew sharper as physicists probed smaller scales and higher energies. Quantum field theory works by treating particles as excitations of invisible fields that stretch across space and time. This picture is extraordinarily successful for the electromagnetic and nuclear forces. But when gravity is forced into the same framework, the mathematics breaks down. Calculations produce infinities that cannot be removed, signaling that something is fundamentally wrong. Physicists needed a new idea, something that could reconcile gravity with quantum mechanics. That idea arrived in the form of string theory. Instead of treating particles as points with no size, string theory proposed that they are tiny one-dimensional loops or segments of vibrating string. Each mode of vibration corresponds to a different particle. Just as the pitch of a guitar string depends on how it vibrates, the mass and charge of a particle depend on the vibration of the fundamental string. Electrons, photons, quarks, and even the graviton, the hypothetical quantum particle of gravity, emerge as different notes on the same instrument. At first, string theory seemed almost too beautiful to be true. It offered a way to unify all forces by reducing them to vibrations of a single kind of object. The mathematics was elegant, and the presence of the graviton in the theory gave hope that quantum gravity could finally be understood. Yet there was a catch, and it was a dramatic one. The equations of string theory simply did not work in the four-dimensional space-time we know. They only made sense if the universe contained more dimensions. Depending on the version of the theory, the number was 10 or 26. In these higher dimensional spaces, the mathematics was consistent. In 4 dimensions, it fell apart. This was not an arbitrary demand. It was built into the very structure of the equations. In 4 dimensions, anomalies appeared, contradictions that made the theory impossible. Only when additional dimensions were included did the equations cancel neatly, preserving the symmetries required for consistency. The implication was clear. If string theory is correct, the universe must contain more dimensions than we perceive. Extra dimensions were no longer optional curiosities. They were necessities. They were necessities. To make sense of why we do not see these dimensions, physicists returned to the idea of compactification, first introduced by Oscar Klein. The extra dimensions, they argued, might be curled up into tiny shapes too small to detect directly. But unlike the simple circle imagined by Klein, string theory required far more complex geometries. These curled-up spaces had to satisfy intricate mathematical constraints to allow the strings to vibrate in ways that matched known particles. The solutions pointed to objects known as Calabi-Yau manifolds, 6-dimensional shapes of extraordinary richness. Each possible manifold defined a different version of physics with its own particles and forces. This revelation opened a new chapter in the story of hidden dimensions. The mathematics of string theory demanded not just one extra dimension, but 6, compactified in ways so complex that entire branches of mathematics grew up to study them. Suddenly, the geometry of higher dimensions was not just an abstract curiosity. It was central to the structure of reality. The shapes of these compact spaces determined the physics we observe. In one shape, particles might have certain masses and charges. In another, the laws of nature might be entirely different. The challenge was enormous. How could one determine which Calabi-Yau manifold corresponded to our universe? The possibilities seemed vast, perhaps numbering in the hundreds of thousands, or even more. This landscape of possible geometries raised both excitement and frustration. On the one hand, string theory provided a framework that could include all known forces and particles. On the other, it offered so many solutions that it was difficult to know which, if any, described reality. Yet the requirement of extra dimensions remained one of the most striking features of the theory. Unlike earlier speculations, which proposed hidden dimensions as a possibility, string theory insisted on them as a necessity. Without them, the mathematics collapsed. With them, the door to unification stood open. The introduction of strings also changed how physicists thought about space and time themselves. If the fundamental constituents of matter are extended objects, then the notion of a point-like particle is only an approximation. At very small scales, the strings smear out interactions, avoiding the infinities that plague point particles. Gravity, once impossible to quantize, emerged naturally as one of the vibrational modes of the string. In this way, extra dimensions were not an exotic addition. They were the very arena in which the strings lived and vibrated, giving rise to everything we see. As this first part of the chapter closes, the stage is set. Kaluza and Klein had imagined one extra dimension as a way to unify gravity and electromagnetism. String theory required 6 extra dimensions, curled into intricate shapes that dictated the laws of physics themselves. What began as speculation was now a demand of consistency. The question was no longer whether extra dimensions could exist, but what their properties might be, and how they shaped the universe we inhabit. The idea that strings require extra dimensions is not just a mathematical curiosity, but a profound statement about the nature of reality. When theorists examined the equations of string theory, they discovered that these hidden dimensions were not arbitrary. They controlled the very properties of the particles we observe. Imagine a violin. The shape of its wooden body determines how the strings resonate, giving each note its timbre. In the same way, the shape of the compactified dimensions determines how fundamental strings vibrate, setting the spectrum of particles and forces in the universe. This realization shifted the question. Physicists no longer asked simply whether extra dimensions exist. They now asked what shape those dimensions take, and why that shape produces the universe we inhabit, rather than some other. The candidates for these hidden geometries were called Calabi-Yau manifolds, named after mathematicians Eugenio Calabi and Xing-Tung Yau. These 6-dimensional spaces are complex, twisted shapes that satisfy the conditions required by string theory. They are so intricate that even drawing a shadow of 1 in 3 dimensions is nearly impossible. Yet their mathematical properties allow strings to vibrate in consistent, stable ways. The variety of Calabi-Yau manifolds is enormous. Each possible shape defines a different version of physics, with different particle masses, charges, and interactions. This vast range of possibilities became known as the string landscape. In principle, the landscape might contain hundreds of thousands, or even millions of solutions. Some physicists saw this as a problem, fearing that a theory with so many possible outcomes might not make unique predictions. Others saw it as an opportunity, suggesting that our universe is just one valley in a vast multiverse of possibilities, each with its own compactified dimensions and physical laws. At the same time, the mathematics of string theory revealed connections to symmetry that seemed too deep to ignore. Symmetry lies at the heart of physics. Conservation of energy arises from the symmetry of time. Conservation of momentum arises from the symmetry of space. In quantum field theory, the symmetries of gauge fields dictate the interactions of particles. In string theory, the extra dimensions provide new types of symmetry, allowing forces to unify in ways that would be impossible in 4 dimensions alone. Supersymmetry was one such idea. It proposed that every particle we know has a partner particle with different spin properties. While no supersymmetric particle has been detected so far, the mathematics of string theory requires them for consistency. These partner particles could stabilize the compact dimensions and cancel the infinities that plague quantum gravity. Supersymmetry also offered a natural candidate for dark matter, the invisible substance that makes up most of the mass of the universe. Though unconfirmed, the possibility that hidden dimensions and supersymmetry are linked gave physicists hope that future experiments might provide evidence. String theory also suggested new ways of looking at black holes. In 4-dimensional relativity, black holes are regions where gravity is so strong that nothing can escape. In string theory, they can be described as collections of strings and brains, higher dimensional objects that generalize the idea of strings. Remarkably, calculations of black hole entropy in string theory matched predictions made decades earlier by Stephen Hawking and Jacob Bekenstein. This agreement between independent approaches hinted that string theory might indeed capture something real about the universe, and that extra dimensions were playing a hidden but essential role. The presence of hidden dimensions also influenced cosmology. Some models proposed that the early universe underwent a phase of compactification, where the extra dimensions curled up, while the familiar 3 expanded. Others suggested that the collisions of higher dimensional brains might have sparked the Big Bang itself. Though speculative, these ideas showed that extra dimensions were not just mathematical decorations. They could shape the largest events in cosmic history. Yet string theory faced a fundamental challenge. How could one ever test it? The strings themselves are thought to be on the order of the Planck length, far beyond the reach of current experiments. The compactified dimensions are equally small, making them invisible to direct observation. Critics argued that a theory without testable predictions risks drifting away from science. Supporters countered that string theory was not a finished product but a framework, one that might eventually make predictions as it matured. They pointed to indirect evidence, such as the possible signatures of extra dimensions in high-energy particle collisions, or in subtle deviations from Newton's law of gravity at short distances. Despite the difficulties, the requirement of extra dimensions remained one of string theory's most striking features. No other theory of quantum gravity has demanded such a radical change in our picture of reality. The fact that the mathematics only works in 10 dimensions seems too precise to dismiss as coincidence. Whether or not string theory turns out to be the final word, it demonstrated that hidden dimensions could no longer be regarded as fringe speculation. They had become central to the most ambitious effort yet to unify the forces of nature. As this part closes, the story of string theory stands at a crossroads. On one side is the elegance of the mathematics, with its demand for extra dimensions, Calabi-Yau, manifolds, and supersymmetry. On the other side is the challenge of evidence, the difficulty of testing predictions that lie beyond current technology. Between these poles stretches the path of modern theoretical physics, a path that continues to be shaped by the idea that reality may be far larger and richer than what our senses reveal. The evolution of string theory did not end with the discovery that it required extra dimensions. In the 1980s and 90s, physicists realized that the story was even more intricate than they had imagined. For years, several different versions of string theory had been developed. Each had its own equations, its own properties, and its own vision of how strings behaved in higher dimensional space. At first, these versions looked like competing theories, but then a surprising realization emerged. They were not separate at all. They were different faces of a deeper, unified framework. This unification became known as M-theory. The M has been said to stand for membrane, for mother, or for mystery, depending on who you ask. What mattered most was that M-theory extended the picture of strings into an even richer landscape. Instead of being limited to one-dimensional strings, the theory allowed for higher dimensional objects called branes. A brane can have any number of dimensions. A two-brane is like a membrane stretched across space. A three-brane extends in 3 directions. Our entire universe, according to some versions of the theory, could be a 3-brane, floating in a higher dimensional bulk. In this framework, the number of dimensions increased again. While string theory required 10, M-theory suggested 11. The extra dimension provided a way to unify the different string theories, showing that they were approximations of a larger structure. Once again, mathematics pointed to hidden directions of space as essential for consistency. Once again, physicists were forced to confront the possibility that reality is vastly richer than it appears. The idea of branes opened new possibilities for explaining physical phenomena. For example, gravity might be weak not because it is inherently feeble, but because it spreads out into the higher dimensional bulk. The other forces, confined to our 3-brane, would appear strong in comparison. This picture, developed in models such as the Randall-Sundrum scenarios, suggested that extra dimensions might not be curled up to tiny scales after all. They could be large or even infinite, warped in such a way that we experience only a slice of them. These models also suggested new experimental tests. If gravity can leak into higher dimensions, then its strength might deviate from the familiar inverse square law at very short distances. Experiments with sensitive torsion balances have sought such deviations, though none have yet been found. High-energy particle colliders might also reveal microscopic black holes, a possible signature of large extra dimensions. So far, no such events have been detected, but the search continues. Another striking development was the connection between string theory and quantum field theory through what is known as the ADS-CFT correspondence. Proposed by Juan Maldacena in 1997, it suggested that a theory of gravity in a higher dimensional curved space could be equivalent to a quantum field theory without gravity on the boundary of that space. This duality provided powerful new tools for studying black holes, particle physics, and even condensed matter systems. Once again, extra dimensions played a central role, not as physical spaces we can travel through, but as mathematical arenas in which the laws of physics could be expressed in new ways. M-theory also deepened the connection between cosmology and hidden dimensions. Some models proposed that the Big Bang itself might have been the result of a collision between brains in higher dimensional space. Others suggested that cosmic inflation, the rapid expansion of the early universe, could be driven by the dynamics of fields moving through extra dimensions. Though speculative, these ideas showed how hidden directions might influence the largest events in cosmic history. The sheer boldness of these ideas captured the imagination of physicists and the public alike. A universe of strings, brains, and extra dimensions challenges every intuition we have, yet it emerges naturally from the mathematics. Whether or not string theory and M-theory ultimately prove correct, they have reshaped the way scientists think about the building blocks of reality. They have shown that geometry, once the study of points and lines, may be the key to unifying all forces, all particles, and perhaps even all universes. As this chapter draws to a close, we see how far the idea of extra dimensions has come. From Kaluza and Klein's single curled-up direction to string theory's 6 compactified shapes to M-theory's 11-dimensional brain worlds, the concept has grown from speculation into one of the central themes of modern theoretical physics. The mathematics insists on these dimensions, even if our senses do not. The challenge now is to find ways to test these bold ideas, to connect the unseen geometry of higher dimensions with the measurable reality of experiments. In the next chapter, we will follow this search into the laboratory and the cosmos. We will see how scientists have devised ingenious tests to look for hidden dimensions, from particle collisions to gravitational wave detectors to precise measurements of gravity itself. The question of whether extra dimensions exist is no longer confined to chalkboards and equations. It has become part of the experimental frontier, where nature will decide whether these extraordinary ideas reflect reality or remain in the realm of mathematics. By the closing years of the 20th century, string theory had already transformed the landscape of theoretical physics. It promised a way to unify all forces. It naturally contained a particle that could act as the graviton, and it insisted on extra dimensions as a requirement of mathematical consistency. But as powerful as it was, string theory seemed fractured. There were 5 different versions of the theory, each with its own details, symmetries, and predictions. For a time, physicists puzzled over which version was correct, wondering if perhaps only one would ultimately survive. Then, in the mid-1990s, a revolution occurred. To the surprise of many, all 5 theories were shown to be connected, not rivals, but different approximations of a deeper and more complete framework. This new framework became known as M-theory. M-theory expanded the picture in profound ways. It revealed that strings were not the only fundamental objects. There were also brains, extended structures, that could have more than one dimension. A 1 brain looked like a string, stretched in one direction. A 2 brain resembled a flexible sheet. A 3 brain extended in 3 spatial directions. And higher brains could exist as well. These brains were not just mathematical artifacts. They played an essential role in the consistency of the theory, carrying charges, defining boundaries, and providing new ways for forces to interact. In this new vision, our universe itself could be a brain. Specifically, some versions of M-theory suggested that we live on a 3 brain, embedded in an 11-dimensional bulk. The familiar particles and forces of the standard model might be confined to this brain, unable to escape it, while gravity alone could spread into the larger bulk. This picture offered a fresh way to explain the weakness of gravity compared to the other forces. If gravity leaks into higher dimensions while the others are trapped, then its apparent feebleness in our four-dimensional world becomes understandable. The mathematics of M-theory pointed to 11 dimensions as the natural stage for the drama of reality. 10 were required by string theory, but an extra one emerged when the different versions were unified. In 11 dimensions, the symmetries of the theory became more complete, and the branes gained their full significance. This echoed a pattern seen before in physics. When apparently separate phenomena are unified, a richer and deeper structure emerges. Just as electricity and magnetism united into electromagnetism, and just as space and time united into space-time, the many versions of string theory united into M-theory. The presence of branes also opened new possibilities for cosmology. If our universe is a brane, then other branes might exist parallel to ours in the higher dimensional bulk. Collisions between branes could produce enormous bursts of energy, perhaps even events resembling the Big Bang. In some scenarios, the history of the cosmos could be shaped not only by the dynamics of matter and energy within our universe, but also by interactions with other branes beyond it. These ideas remain speculative, but they showed the imaginative power of M-theory to recast fundamental questions about origins and fate. Another breakthrough connected M-theory with black hole physics. In the 1970s, Jacob Bekenstein and Stephen Hawking had shown that black holes have entropy, a measure of the information they contain. But the microscopic origin of this entropy remained a mystery. In the 1990s, string theorists used branes to count the possible states of certain black holes. To their astonishment, the numbers matched exactly with the entropy predicted by Hawking and Bekenstein. This result provided one of the strongest hints that string theory and M-theory might capture real features of nature, and that extra dimensions and branes were more than elegant mathematics. The introduction of branes also shifted how physicists imagined hidden dimensions. In Kaluza and Klein's vision, extra dimensions were small circles curled up at microscopic scales. In M-theory, they could also be large and warped, stretching across the bulk in ways that subtly influence our universe. The Randall-Sundrum models, developed in the late 1990s, showed how gravity could be localized on a brane within higher dimensions, creating effects that might be detectable in experiments. These models re-energized the search for experimental signatures of extra dimensions, providing concrete scenarios to test. As this first part of the chapter closes, the story of hidden dimensions has reached a new level. From the single curled-up direction of Kaluza and Klein to the 6 Calabi-Yau shapes of string theory, and now to the 11-dimensional world of M-theory, the concept has grown ever richer. Branes have entered the stage, not as background decorations, but as central actors. They may hold the key to explaining the structure of our universe, the weakness of gravity, and even the nature of black holes. The journey is far from over. In the next part, we will follow the detailed development of brane cosmology, explore how branes might explain features of our universe, and examine how theorists have sought ways to test these bold ideas in laboratories and telescopes. The question remains open, but the vision is breathtaking. A universe that is not isolated, but a brane, adrift in a vast and multi-dimensional sea. In the years after M-theory emerged, the role of branes grew from a mathematical curiosity into a central theme of modern cosmology. If our universe is itself a three-brane, then many of the puzzles of physics might be explained in new ways. The question of why gravity is so weak compared to the other forces became one of the most natural to revisit. Electromagnetism, the strong force, and the weak force might all be confined to our brane, unable to escape into the wider bulk. Gravity, by contrast, could spread freely into all 11 dimensions. To us, it would appear diluted, faint compared to the tightly bound forces that remain trapped. What once seemed like an inexplicable hierarchy might be nothing more than the result of geometry. This idea took concrete form in the late 1990s through the work of Lisa Randall and Raman Sundrum. They proposed models in which our universe sits on a brane within a higher dimensional bulk. In one version, there are two branes separated by a small distance in the 5th dimension, with gravity concentrated on one brane but leaking toward the other. In another, there is a single brane with a warped extra dimension that stretches infinitely but still confines gravity near our world. These scenarios became known as the Randall-Sundrum models, and they showed that hidden dimensions need not always be tiny. They could be large, even infinite, provided their geometry was warped in the right way. The power of these models lay not only in their mathematical elegance, but in their testability. If gravity leaks into extra dimensions, then its strength might deviate from the familiar inverse square law at very short distances. Experiments began to measure the pull of gravity at millimeter and sub-millimeter scales with extraordinary precision. So far, no deviations have been detected, but the very act of probing gravity at such scales marked a new frontier. The search for hidden dimensions was no longer confined to blackboards and chalk. It had entered the laboratory. Brain cosmology also suggested new ways to think about the beginning of the universe. In some scenarios, the Big Bang might have been triggered by the collision of two brains in higher dimensional space. The enormous energy of such a collision could produce the hot, dense conditions we observe at the dawn of time. This idea, known as the ekpyrotic model, offered an alternative to traditional inflationary cosmology. Though still speculative, it highlighted how higher dimensions could provide fresh perspectives on old questions. Another remarkable development was the application of brain ideas to string theory's compactified dimensions. Instead of imagining 6 dimensions curled into Calabi-Yau manifolds that remain hidden and passive, theorists considered the possibility of brains stretching across them, wrapping around their folds, and shaping their geometry. The dynamics of these brains could determine the values of fundamental constants, such as the masses of particles and the strength of forces. In this way, the properties of our universe might be set not by arbitrary numbers, but by the configuration of brains in a higher dimensional space. Brains also played a central role in the study of black holes within M-theory. Certain configurations of brains could be used to build black holes in the theory, allowing physicists to count their microscopic states. The exact match between these counts and the entropy predicted by Hawking's calculations provided some of the strongest evidence yet that M-theory was capturing something real about nature. The success was striking. The entropy of black holes, one of the deepest puzzles in theoretical physics, found an explanation in the vibrations and arrangements of brains. The implications for particle physics were equally bold. If the universe is a brain, then new particles might exist that interact weakly with ordinary matter, but strongly with the higher dimensional bulk. Some of these particles could serve as candidates for dark matter, the invisible substance that outweighs normal matter in galaxies. Others might appear only at energies reachable in future colliders, leaving faint but detectable signatures. Even though direct evidence remains elusive, the possibilities gave experimentalists new targets to search for. The introduction of brains also reshaped the philosophy of physics. It challenged the idea that our universe is the whole of reality. Instead, we might be one slice of a far vaster structure, a brain floating in a multidimensional sea. Other brains might exist nearby, perhaps even parallel to ours, carrying their own universes, with their own particles and laws. While speculative, this vision expanded the imagination of science, suggesting that what we call the universe might be only one part of a much larger whole. As this second part of the chapter draws to a close, it is clear that brains are more than an add-on to string theory. They are fundamental to the way M-theory reshapes our picture of the cosmos. They explain the weakness of gravity. They suggest new beginnings for the universe. They provide insight into black holes, and they offer new directions for experiments. Whether or not M-theory turns out to be the final description of reality, the concept of brains has already changed how physicists think about space, time, and dimensions. The next step is to explore how these bold ideas can be connected more closely with observation. In the final part of this chapter, we will follow the efforts to link brains and hidden dimensions to experiments, from particle colliders to gravitational wave detectors, and consider what it would mean if evidence for extra dimensions were finally found. The effort to connect brains and higher dimensions with experiment has been one of the most ambitious undertakings in modern physics. M-theory and its brain worlds offer a vision that is bold and elegant, but for it to become more than mathematics, it must leave measurable traces. Physicists have spent decades searching for such signatures, designing experiments that could reveal the influence of extra dimensions on the world we inhabit. One of the most direct approaches has been to test gravity itself. According to Newton, the strength of gravity between two masses falls off as the inverse square of the distance between them. This law has been confirmed over scales ranging from planetary orbits down to millimeter distances. But if gravity can spread into higher dimensions, its behavior might deviate from the inverse square law at extremely short ranges. To test this, experimentalists have built delicate torsion balances capable of measuring gravitational forces between tiny masses separated by fractions of a millimeter. These experiments are feats of engineering designed to detect incredibly small effects while shielding against stray electromagnetic forces and vibrations. So far, no deviation has been seen, but the limits have tightened. If extra dimensions exist, they must either be smaller or more strongly warped than the simplest models predict. Another line of investigation comes from particle physics. If our universe is a brain embedded in a higher dimensional bulk, then collisions at very high energies might create excitations that reveal the presence of extra dimensions. One dramatic possibility is the production of microscopic black holes at particle colliders. In higher dimensional theories, the threshold energy for black hole formation could be much lower than in four-dimensional relativity, placing it within reach of machines like the Large Hadron Collider. Such black holes would evaporate almost instantly, spraying out a characteristic pattern of particles. The absence of these events so far has again pushed the scale of extra dimensions higher, narrowing the window but not closing it entirely. Cosmology has also become a laboratory for testing brain ideas. The early universe, with its extreme energies and rapid expansion, could have been shaped by higher dimensional dynamics. If brain collisions played a role in the Big Bang, or if inflation was driven by fields moving through extra dimensions, the fingerprints of these events might be visible in the cosmic microwave background. Precision measurements of this ancient radiation have already provided hints about inflation and structure formation. The challenge is to distinguish signatures of extra dimensions from the many other processes that occurred in the first moments of cosmic history. Gravitational waves add another tool to the search. If extra dimensions exist, they could alter the way these ripples in space-time propagate. Detectors like LIGO and Virgo have already observed waves from merging black holes and neutron stars. Future generations of detectors, more sensitive and spread across space, might detect subtle deviations in the speed, strength, or polarization of these waves. Such deviations could point toward the influence of hidden dimensions. Even if no evidence has yet emerged, the search itself is reshaping the boundary between theory and experiment. By translating the bold ideas of M-theory into testable predictions, physicists are grounding speculation in measurable reality. Each null result narrows the possibilities, forcing theorists to refine their models. Each improvement in technology brings us closer to scales where hidden dimensions might reveal themselves. Beyond experiment, brains have left their mark on the philosophy of science. They remind us that our universe may not be the whole of existence, that the laws we take for granted may be shaped by geometry in realms beyond perception. The notion that we live on a brain, one of countless others drifting in a higher dimensional bulk, challenges the traditional idea of a single, self-contained cosmos. It raises questions not only about physics but about meaning. If other brains exist, could they hold other universes, with other stars, planets, and perhaps even other forms of life? For now, these questions remain open. What is certain is that M-theory and its brains have transformed the way physicists think about unification. They offer a vision in which geometry is the foundation of all forces, in which black holes and the Big Bang alike are shaped by higher dimensions, and in which gravity's weakness is not a flaw, but a clue. Whether or not experiments confirm this vision, the journey has expanded our imagination and deepened our understanding of what reality might be. As this chapter ends, the story moves from theory to observation. The next chapter will follow the ongoing search for physical evidence of extra dimensions, from the smallest scales probed in laboratories to the largest scales mapped in the cosmos. The question is no longer whether extra dimensions are mathematically possible, It is whether nature itself has chosen to use them. For centuries, the idea of hidden dimensions belonged to the realm of mathematics and imagination. Kaluza and Klein had hinted at their physical reality. String theory had demanded them. And M-theory had placed our entire universe on a brain suspended in an 11-dimensional bulk. But a theory, no matter how elegant, must face the test of nature. Physics is not complete until predictions meet experiment. The question, then, became clear. If extra dimensions exist, how could we possibly detect them? One of the most straightforward approaches is to test gravity itself. Newton's law tells us that the gravitational force between two masses decreases as the inverse square of the distance between them. Einstein's relativity refines this picture but preserves the same basic dependence at everyday scales. Yet, if gravity can leak into extra dimensions, the rule may change at very small distances. Instead of falling off as the inverse square, it could drop more steeply or flatten in unexpected ways. The challenge is that gravity is already the weakest of the forces, and measuring it at tiny scales requires extraordinary precision. Physicists built delicate torsion balance experiments to tackle this problem. In these devices, small test masses are suspended on thin wires, free to twist, in response to tiny gravitational forces. By carefully shielding the apparatus from vibrations, magnetic influences, and even the movement of air, researchers pushed the limits of measurement down to the millimeter and then to the sub-millimeter scale. If extra dimensions were as large as a fraction of a millimeter, such experiments would have detected deviations from Newton's law. None have been found. This result does not rule out hidden dimensions altogether, but it forces them to be either smaller, more warped, or more subtle than the simplest models suggest. Another line of search comes from high-energy particle collisions. If space-time has more dimensions than we perceive, then smashing particles together at sufficient energies could reveal them. One striking prediction is the possibility of creating microscopic black holes. In higher dimensional theories, the energy required to form such black holes is lower than in four-dimensional relativity. A collider, like the Large Hadron Collider, could, in principle, reach the necessary energies. If created, these black holes would not pose any danger. They would evaporate almost instantly, releasing a spray of particles in distinctive patterns. So far, no such events have been observed. Each absence raises the threshold, telling physicists that if hidden dimensions exist, they must influence reality at scales beyond what current colliders can reach. Cosmology provides another testing ground. The early universe was an arena of extreme energies, far beyond what any laboratory can achieve. If extra dimensions shaped the birth of the cosmos, their fingerprints might remain in the cosmic microwave background, the faint afterglow of the Big Bang. Satellites like COBE, WMAP, and Planck have mapped this radiation with exquisite detail. They revealed tiny ripples in temperature, traces of the earliest fluctuations that grew into galaxies. Some theories predict that extra dimensions would leave subtle imprints in these ripples, perhaps in their polarization patterns or in correlations across the sky. So far, the data has not demanded such an explanation, but the possibility remains open. Gravitational waves add a new frontier. These ripples in space-time, first directly detected in 2015, travel across the universe, carrying information about violent events like merging black holes and neutron stars. In a universe with extra dimensions, gravitational waves might behave differently, leaking into the bulk or returning with altered signatures. Future detectors, more sensitive and more widespread than today's, may be able to pick up such deviations. If found, they would provide some of the strongest evidence yet for hidden dimensions. The search for extra dimensions is a story of ingenuity and persistence. Each experiment pushes deeper into the unknown, narrowing the possibilities. Each null result is not a failure but a clue, guiding theorists toward more precise models. The dream of finding a signal remains alive. It might come from a small deviation in a gravitational experiment, from an unexpected event in a collider, from a subtle pattern in the cosmic microwave background, or from a whisper in the fabric of gravitational waves. As this part of the chapter closes, the divide between theory and experiment begins to narrow. Hidden dimensions are no longer just the domain of chalkboard equations and abstract manifolds. They are subjects of real, testable science. The coming years may bring discoveries that transform speculation into evidence, or they may push the boundaries of hidden dimensions further from reach. Either way, the search is underway, and it is reshaping the way we think about the very fabric of reality. The pursuit of extra dimensions through high-energy physics has become one of the most daring enterprises in science. Particle accelerators like the Large Hadron Collider were not built solely to hunt for hidden dimensions, but they provide a unique stage where the extreme energies of the early universe can be recreated, if only for the briefest moments. When protons are hurled together at nearly the speed of light, the collision zone becomes a furnace of pure energy, hot enough to spawn heavy particles or even distort space-time itself. If extra dimensions exist, these collisions might provide the first glimpse. One prediction concerns the production of gravitons, the hypothetical quantum particles that carry the force of gravity. In a universe with extra dimensions, gravitons might be able to slip away from our brain into the higher dimensional bulk. To detectors on Earth, this would look like missing energy. After a collision, energy must always balance. If a portion vanishes without explanation, it may have escaped into a hidden dimension. Physicists have combed through countless collision events, searching for such missing energy signatures. So far, none have been found, but the sensitivity of these searches continues to grow. The possibility of microscopic black holes remains another striking test. In ordinary four-dimensional physics, creating a black hole would require far more energy than any collider can achieve. But if extra dimensions exist, the threshold could be much lower. A collision might briefly compress enough energy into a tiny region to form a black hole smaller than an atom. These black holes would not persist. They would evaporate almost instantly through Hawking radiation, producing a shower of particles with a unique distribution. This distinctive signature would stand out from the background of ordinary collisions. Despite much anticipation, no such events have been observed at the Large Hadron Collider. Each round of data places tighter limits on the size and shape of extra dimensions, pushing them further out of reach. Cosmological observations offer a different path. The universe itself is the ultimate experiment, a vast laboratory that has been running for nearly 14 billion years. If extra dimensions influence the early moments of the cosmos, their traces might still be visible. Inflation, the rapid expansion that occurred fractions of a second after the Big Bang, may have been driven by fields moving through higher dimensions. If so, the ripples they produced could still be etched into the cosmic microwave background. Observatories have searched for these patterns, particularly in the polarization of the background light. While no clear evidence has emerged, the effort continues with ever more sensitive instruments. Another window comes from the distribution of galaxies across space. Structures on the largest scales reflect the physics of the early universe. If extra dimensions affected how matter clumped together, they could leave subtle signatures in the patterns we observe today. Surveys mapping millions of galaxies aim to detect these signals, testing models of higher dimensional cosmology against the observed universe. Gravitational waves extend this effort into a new domain. When black holes merge, the waves they release ripple across the universe, stretching and squeezing space-time as they pass. If extra dimensions exist, these waves might lose energy into the bulk, arrive slightly altered, or reveal additional polarizations beyond what Einstein's theory predicts. The detectors now operating are sensitive to some of these possibilities, but future instruments, including space-based observatories, will be far more powerful. They may allow us to hear whispers from dimensions that lie beyond sight. Each of these searches highlights the same tension. The mathematics of string theory and M theory insists on hidden dimensions, but nature has yet to reveal them. Some physicists see this as a sign that the theories are incomplete, still awaiting the key insight that will connect them to experiment. Others see it as an invitation to build more sensitive detectors, to probe higher energies and smaller scales, to push the boundaries of observation further. The absence of evidence is not evidence of absence. It may be that extra dimensions are real, but hidden too deeply for current technology to uncover. Or it may be that they manifest in ways we have not yet imagined. The history of science teaches humility. For centuries, the existence of atoms was debated without proof. For decades, gravitational waves were predicted before they were finally detected. Hidden dimensions may follow the same path, eluding us until the right experiment at the right moment uncovers them. As this part of the chapter closes, the pursuit of evidence stands at a delicate balance. The equations demand extra dimensions, the experiments search for them, but the signals remain silent. The next frontier may lie in even more ambitious experiments, in new colliders, space telescopes, and gravitational wave observatories. The search continues, guided by the conviction that the deepest truths of nature, however hidden, can be revealed by patient observation. The quest for hidden dimensions is as much about patience as it is about imagination. Each new generation of experiments has pushed deeper into unexplored territory, testing ideas that once seemed impossible to probe. The results so far have been consistent with the familiar four-dimensional picture, but this consistency itself is informative. It tells us that if extra dimensions exist, they must be more subtle than early models suggested. They cannot be as large as a fraction of a millimeter. They cannot allow gravity to deviate from Newton's law in ways already ruled out. They cannot produce black holes at the energies probed by today's colliders. In this sense, every null result narrows the possibilities, guiding theorists toward more refined and resilient models. Yet the search is far from over. The next decades promise a wave of new experiments with unprecedented sensitivity. Gravitational wave astronomy is still in its infancy, but future detectors in space, free from the noise of Earth, will be able to measure the cosmos with exquisite precision. They may detect signals from the earliest moments after the Big Bang, moments when extra dimensions could have played a decisive role. Particle physics may also deliver new insights, whether through upgrades to existing colliders or through the construction of machines even more powerful than the Large Hadron Collider. Each step upward in energy opens a new window onto reality. Cosmology remains perhaps the most promising arena. The cosmic microwave background is a relic of the early universe, but it is not the only one. Neutrinos, the ghostly particles that pass almost unhindered through matter, carry information from epochs even earlier. Primordial gravitational waves, if detected, would offer a direct view into the physics of the Planck era, when quantum gravity and extra dimensions may have shaped the unfolding cosmos. These signals are faint and difficult to detect, but not beyond the reach of human ingenuity. The challenge of testing higher dimensions has also inspired creative thinking about indirect evidence. Some physicists have suggested that dark matter might be a hint of particles leaking from or interacting with extra dimensions. Others propose that dark energy, the mysterious force driving the accelerated expansion of the universe, could be the effect of higher dimensional geometry. While these ideas remain speculative, they highlight the possibility that the clues we seek may already be visible, hiding in puzzles we have yet to solve. Still, it is possible that extra dimensions will never leave obvious traces in experiments. They may be forever compactified at scales beyond reach, their influence limited to the structure of the equations rather than to observable signatures. If that is the case, the question becomes philosophical as well as scientific. Should we accept a picture of reality that requires hidden dimensions if they can never be tested directly? Or should we demand that even the boldest theories meet the same standard as all science, grounded in observation? This debate continues within physics, reflecting both the power and the limits of human inquiry. What cannot be denied is the role the search has already played in advancing technology and thought. Experiments designed to probe gravity at the smallest scales have pushed the limits of precision engineering. Colliders have expanded our ability to manipulate energy and matter at the highest intensities. Cosmological observations have mapped the universe with detail unimaginable a century ago. Even without direct evidence of extra dimensions, the pursuit has deepened our understanding of the cosmos and sharpened the questions we ask. As this chapter closes, we return to the central theme. Extra dimensions are no longer only the domain of mathematics. They have entered the realm of testable science. The evidence has not yet come, but the search has only begun. Whether the universe chooses to reveal hidden dimensions or not, the journey of discovery itself is reshaping our view of reality. The next chapters will consider what the existence of hidden dimensions would mean for physics, for cosmology, and for our understanding of humanity's place in the universe. The search for hidden dimensions is not only about detecting them directly, it is also about asking what their existence would mean for the deepest questions in science. If extra dimensions are real, then they are not merely hidden directions of space. They would reshape the foundations of physics, altering how we understand forces, particles, and the history of the cosmos itself. The most immediate consequence lies with gravity. For more than a century, physicists have puzzled over why gravity is so weak compared to the other forces. The electromagnetic force holds atoms together. The strong force binds protons and neutrons. The weak force drives radioactive decay. Each of these is enormously more powerful than gravity. A small magnet can lift a paperclip against the pull of the entire Earth. The hierarchy between gravity and the other forces spans nearly 40 orders of magnitude. Hidden dimensions offer a natural explanation. If gravity is not confined to our familiar space-time but spreads into extra dimensions, then its apparent weakness is not fundamental. It is diluted by its presence in the larger bulk. What seems puzzling in 4 dimensions may be natural in higher ones. This insight carries profound implications for unification. For decades, physicists have dreamed of combining all forces into a single framework. The Standard Model has already unified electromagnetism with the weak force, and it describes the strong force with precision. But gravity has always resisted inclusion. Extra dimensions provide a possible path. If all forces arise from geometry in higher dimensions, then their apparent differences may be illusions of perspective. What we call distinct forces could be different aspects of a single higher dimensional reality. String theory embodies this idea most directly. By treating particles as vibrations of tiny strings, it unifies gravity and quantum mechanics in a single framework. The requirement of extra dimensions is not a flaw, but the very feature that allows the unification to work. Without them, the equations collapse. With them, the pieces of physics begin to fit together. The Kaluza-Klein vision of uniting gravity and electromagnetism was only the beginning. In string theory and M theory, hidden dimensions become the stage upon which all forces and particles are written. Another consequence concerns quantum gravity itself. One of the deepest problems in physics is how to reconcile Einstein's relativity with quantum mechanics. Black holes are the sharpest example of this conflict. According to relativity, nothing escapes a black hole. According to quantum theory, information can never be destroyed. Hawking radiation, predicted in the 1970s, only deepened the puzzle. It suggested that black holes slowly evaporate, potentially erasing the information they contain. Hidden dimensions provide new tools for addressing this paradox. In string theory, black holes can be described in terms of branes and strings, allowing physicists to count their microscopic states. The agreement between this counting and the entropy predicted by Hawking and Bekenstein remains one of the strongest pieces of evidence that higher dimensional theories may capture real aspects of the universe. The consequences extend into cosmology. The accelerated expansion of the universe, attributed to dark energy, may be influenced by the geometry of hidden dimensions. Some models propose that the energy of compactified dimensions contributes to the vacuum energy of our universe. Others suggest that the dynamics of branes in the bulk drive cosmic acceleration. While no single explanation has been confirmed, these ideas show how higher dimensions could affect not only the microphysics of particles, but also the fate of the entire cosmos. Even inflation, the rapid expansion of the early universe, may be linked to hidden dimensions. In brane inflation scenarios, the separation and interaction of branes in higher dimensions provide the energy needed to drive inflation. The collisions and movements of these branes could leave imprints in the cosmic microwave background, signatures that future observations might detect. Hidden dimensions also influence the way physicists think about symmetry. Supersymmetry, the idea that every particle has a partner, finds a natural home in higher dimensional theories. Supersymmetric partners could stabilize the geometry of compactified spaces and explain why the masses of particles take the values they do. Though supersymmetry has not yet been observed, its link to higher dimensions ensures that it remains a central concept in modern physics. As this first part of the chapter closes, the message is clear. The existence of hidden dimensions would not be a minor addition to physics. It would be a revolution. It would explain why gravity is weak, provide a path to unification, offer tools for understanding black holes, and reshape our view of the universe's expansion and origin. The search for extra dimensions is not only about whether they exist, it is about what they would mean if they do. The dream of unification has always guided physics. From Newton's laws that tied the motion of apples and planets together, to Maxwell's equations that joined electricity and magnetism, to Einstein's relativity that wove space and time into a single fabric, each step forward has revealed a hidden unity behind phenomena once thought separate. Extra dimensions carry this dream further. They suggest that the divisions we see between gravity, electromagnetism, the weak force, and the strong force are not fundamental, but the result of our limited perspective. In a higher dimensional space, these forces might be different aspects of one geometry, their differences, an illusion of confinement to 4 dimensions. In this vision, the equations of physics are simplified. What looks like a zoo of particles and forces in 4 dimensions may emerge from the vibrations of strings in 10 or 11 dimensions. The strong force, which binds quarks into protons and neutrons, and the weak force, which governs radioactive decay, appear distinct in our world. But in a higher dimensional framework, they may be unified by symmetries invisible to us. The complexity of the Standard Model, with its many parameters and particle types, might be the shadow of a far simpler structure in hidden dimensions. This idea carries profound consequences for quantum gravity. The clash between general relativity and quantum mechanics has resisted resolution for nearly a century. Attempts to quantize gravity directly have run into infinities and contradictions. Extra dimensions offer a way around these obstacles. By replacing point particles with strings and branes that extend into higher dimensions, the interactions that produce infinities in quantum field theory are smoothed out. Instead of singular points, the strings smear interactions across a tiny but finite scale. This regularization is only possible because of the additional dimensions that provide space for the strings to vibrate. In this way, the existence of hidden dimensions is tied directly to the possibility of a consistent theory of quantum gravity. The consequences also reach into the heart of black hole physics. In 4 dimensions, black holes are described by only a few parameters: mass, charge, and spin. Yet the entropy of a black hole suggests a vast number of microscopic states hidden within. How can these states be counted? String theory provided an answer. By modeling certain black holes as configurations of branes and strings wrapped around compact dimensions, physicists were able to count the number of distinct arrangements. The result matched perfectly with the entropy predicted by Hawking's calculations. This was not only a triumph for string theory, but also a demonstration that higher dimensions play a crucial role in the microscopic structure of space and time. Cosmology, too, takes on a new light in the presence of hidden dimensions. The accelerated expansion of the universe, attributed to dark energy, may arise from the vacuum energy of compactified spaces. The precise geometry of the extra dimensions could determine the effective cosmological constant in our 4-dimensional universe. In some models, the rolling or shifting of fields across higher dimensions can mimic dark energy, providing a dynamic explanation for cosmic acceleration. Others propose that the collision or separation of branes in the bulk could drive cycles of expansion and contraction, offering an alternative to the traditional picture of a singular Big Bang. These ideas, while speculative, demonstrate the richness of higher dimensional physics. They show that hidden dimensions are not minor adjustments, but central players in the drama of the cosmos. They influence the smallest particles and the largest structures alike. They connect the physics of black holes to the expansion of the universe, weaving together questions that once seemed unrelated. If confirmed, the discovery of extra dimensions would be more than a scientific result. It would mark a new chapter in humanity's understanding of existence. It would show that our senses reveal only a slice of reality, that the universe is deeper and richer than the stage on which we live. Just as past unifications reshaped not only science but philosophy, the recognition of hidden dimensions would transform our worldview. As this part of the chapter closes, the scope of the consequences becomes clear. Extra dimensions are not just hidden directions waiting to be found. They are the foundation upon which unification, quantum gravity, black hole physics, and cosmology may ultimately rest. The next part will explore how these consequences affect our understanding of humanity's place in the cosmos, and why the search for hidden dimensions is as much about meaning as it is about measurement. The existence of hidden dimensions would not only reshape equations, it would reshape the way humanity sees itself in the universe. For centuries, each great scientific revolution has forced us to reconsider our place in the cosmos. The Copernican shift moved Earth from the center of creation to a planet orbiting an ordinary star. Newton's laws revealed that the same gravity guiding falling apples governed the motion of planets. Relativity taught us that space and time themselves are not fixed, but can bend and stretch. Quantum mechanics showed us a world of uncertainty, where particles exist in clouds of possibility rather than precise locations. The recognition of hidden dimensions would mark another turning point, challenging the idea that reality is confined to what our senses can perceive. If extra dimensions are real, then our entire experience of existence is a projection, a shadow of a richer structure. What we call the universe may be just a brain, a slice within a higher dimensional bulk. Gravity's weakness, the values of particle masses, even the acceleration of cosmic expansion may all be consequences of geometry in hidden spaces we can never walk through. The implications are profound. It suggests that the laws of physics we have uncovered are not ultimate but emergent, shaped by the unseen architecture of extra dimensions. Such a picture invites philosophical reflection. Are these hidden dimensions part of reality if we can never directly perceive them? The history of science suggests that reality often extends far beyond perception. Atoms were debated for centuries before experiments confirmed them. Radio waves were once invisible, their existence inferred only from equations before technology made them tangible. Gravitational waves were predicted for 100 years before detectors heard them. In the same way, extra dimensions may be real even if direct evidence remains distant. Reality does not wait for human senses to catch up. The recognition of hidden dimensions would also reshape cosmology's grand narratives. If our universe is one brain among many, then the cosmos itself is larger than anything we have imagined. Other brains could carry other universes, perhaps with laws of physics entirely different from ours. The multiverse, once speculative, would gain a new physical foundation. Whether or not these other universes can ever interact with ours, their existence would transform the meaning of the universe. We would no longer be inhabitants of all that exists, but citizens of a far vaster, multidimensional structure. For physics, the consequences would be practical as well as philosophical. Hidden dimensions could provide the framework for a unified theory of everything, a goal that has driven science for over a century. They could explain the puzzles of dark matter and dark energy, the mysteries of black holes, and the details of the Big Bang. But for humanity as a whole, the consequences are existential. They remind us that what we perceive is not all there is. They humble us, showing that the universe is always more mysterious and more expansive than our imaginations allow. As this chapter closes, the lesson is clear. Hidden dimensions are not only about unifying equations or solving technical problems in physics. They are about expanding our vision of reality. They tell us that our place in the cosmos is even smaller and stranger than we thought, and yet also more connected to a vast structure of unimaginable richness. The journey toward discovering or disproving them is not only a scientific quest, but a human one, an attempt to push against the boundaries of perception and knowledge. In the next chapter, we will turn from consequences to origins. We will explore how hidden dimensions may have shaped the earliest moments of the cosmos, and how their influence might still be written in the structure of the universe today. The story of hidden dimensions is not only about the present structure of the cosmos, it also reaches back to the very beginning, to the first instance after the Big Bang, when the universe, as we know it, was born. At those unimaginable energies and densities, the familiar laws of physics break down. General relativity and quantum mechanics clash, producing infinities instead of answers. If ever there was a stage where higher dimensions could reveal themselves, it was in those first moments of creation. The Big Bang Theory describes how the universe expanded from an incredibly hot and dense state nearly 14 billion years ago. In its earliest fractions of a second, it underwent a period of rapid inflation, expanding faster than the speed of light, smoothing out irregularities and seeding the cosmos with the fluctuations that would grow into galaxies. But what drove this expansion? Why did the universe inflate at all? Conventional inflation theory introduces a hypothetical field, the inflaton, whose energy caused the rapid growth. Yet hidden dimensions provide another possibility. In some models, inflation is not driven by a simple field, but by the dynamics of branes in higher dimensional space. Imagine two branes drifting in the bulk. Their movement toward each other stores energy, like two massive plates attracting across a void. When they collide, that energy is released, producing a burst of heat and radiation that resembles the Big Bang. This idea, called brane inflation, recasts the origin of the universe as the result of higher dimensional interactions. What looks to us like a singularity may be the aftermath of a cosmic collision in an unseen dimension. Other scenarios go further, suggesting that the universe itself may be cyclic. In the ekpyrotic model, the cosmos undergoes an endless sequence of brane collisions and expansions. Each cycle ends with a collision that produces a burst of matter and radiation, followed by expansion, cooling, and the formation of galaxies. Billions of years later, the branes collide again, beginning the cycle anew. This vision replaces the singular origin of the universe with an eternal rhythm of higher dimensional events. Even in less speculative frameworks, extra dimensions may have shaped inflation. In certain string theory models, the energy stored in the compactified dimensions contributes to the vacuum energy that drives expansion. Fields moving through these curled-up spaces may create the conditions needed for inflation to occur. The details of how the extra dimensions are shaped the topology of the Calabi-Yau manifold, the presence of branes wrapped around it, can influence the duration and intensity of inflation. In this way, the geometry of hidden spaces, billions of times smaller than an atom, may have determined the size and structure of the entire observable universe. Cosmologists search for evidence of these ideas in the cosmic microwave background. This faint afterglow of the Big Bang carries the imprint of the earliest fluctuations in the universe. Patterns in its polarization and correlations across the sky may reveal whether inflation was driven by a simple scalar field or by more complex higher dimensional dynamics. Some models predict small but distinctive features, such as non-Gaussian fluctuations or subtle asymmetries. While no clear evidence has yet pointed to extra dimensions, the precision of measurements has grown steadily. Future missions may provide the sensitivity needed to distinguish between competing theories. Another possible clue lies in primordial gravitational waves. These ripples in space-time would have been produced during inflation, carrying information from the earliest instance of the universe. If extra dimensions played a role, they may have altered the spectrum of these waves, changing their strength, frequency, or polarization. Detecting primordial gravitational waves remains one of the great goals of modern cosmology. If they are found, and if their properties match the predictions of higher dimensional models, it would provide strong evidence that hidden dimensions shaped the birth of the cosmos. The early universe is a natural place to search for the fingerprints of higher dimensions. At energies far beyond what colliders can reach, the laws of physics may reveal their full form. Whether through brane collisions, compactification dynamics, or the influence of fields moving in extra dimensions, the first moments after the Big Bang remain the most promising window into the unseen structure of reality. As this first part of the chapter ends, the story turns from possibility to pursuit. How can we connect these grand ideas with observation? How can we read the faint signals left in the sky? the whisper of gravitational waves, or the structure of galaxies, to learn about hidden dimensions. The next part will explore the ongoing effort to match theory with evidence and to decide whether the early universe truly bears the mark of higher dimensions. The early universe is the ultimate testing ground for theories of hidden dimensions because it reached energies that no human experiment can reproduce. The collisions inside the most powerful accelerators today pale in comparison to the conditions that prevailed within the first trillionth of a second after the Big Bang. At those scales, gravity and quantum mechanics were not separate actors but part of the same play. If extra dimensions exist, they would have been active participants in shaping the universe we see. One of the clearest ways higher dimensions may have influenced the cosmos is through inflation. The standard picture imagines a single field, the inflaton, filling space with uniform energy that drove expansion. But this picture, though simple, leaves unanswered questions. Why did inflation end? Why did it last the right amount of time to create the universe we observe? Hidden dimensions provide alternative explanations. In brain inflation models, the rapid expansion comes from the motion of brains across higher dimensional space. The potential energy stored in their separation acts like the inflaton field. As the brains move closer, expansion accelerates. When they collide, the stored energy is released, heating the universe and ending inflation. This picture has the advantage of grounding inflation in geometry rather than inventing a new field without context. It also makes testable predictions. The fluctuations produced in brain inflation may have different statistical properties than those from conventional models. They may generate distinctive non-Gaussian patterns in the cosmic microwave background, correlations between regions of the sky that would otherwise be random. Observatories have searched for such patterns, and while none have been conclusively detected, the effort continues, with instruments of increasing sensitivity. The ekpyrotic and cyclic models add another layer. Instead of a single Big Bang, they propose a series of cosmic cycles, each triggered by brain collisions. These models address some puzzles of cosmology, such as why the universe is so uniform on large scales. They also suggest that what we call the beginning may be just one act in an eternal drama. If true, the geometry of higher dimensions is not just a backdrop, but the stage upon which the history of universes unfolds endlessly. Testing such ideas is difficult, but not impossible. Certain signatures, like specific gravitational wave spectra, could distinguish a cyclic cosmos from one born in a single inflationary burst. Compactification also plays a role in cosmology. As the universe cooled, the extra dimensions required by string theory may have curled up into their present shapes. The process of compactification could leave traces, such as relic particles or fields that survive from that era. These relics might contribute to dark matter or affect the way the universe expanded at later times. The detailed shape of the compactified dimensions may even determine fundamental constants, like the strength of forces and the masses of particles. In this sense, the geometry of hidden dimensions could be responsible for the entire structure of the physical world. Cosmologists look for these clues in large-scale surveys of galaxies. The way matter clusters, across billions of light years, encodes information about the physics of the early universe. If extra dimensions influenced inflation or compactification, the patterns of clustering might reflect those effects. Future surveys mapping millions of galaxies aim to test these possibilities, comparing observations against the predictions of higher dimensional models. Another frontier is primordial gravitational waves. These ripples in space-time, produced during inflation, would carry direct information from the earliest instants. The challenge is that their signals are faint, buried under foreground noise from galaxies, dust, and other astrophysical sources. Yet experiments continue to push the limits, searching for the subtle polarization patterns they would imprint in the cosmic microwave background. A detection would be a breakthrough, opening a window onto energies where extra dimensions might be unavoidable. Even the mysterious phenomena of dark energy and dark matter may be connected to higher dimensions. Some theories suggest that dark energy arises from the vacuum energy of compactified dimensions, while dark matter could be particles interacting across brains or leaking into the bulk. If these ideas are correct, then the hidden dimensions are not distant curiosities, but active ingredients in the structure and fate of the universe. As this second part of the chapter closes, the search for cosmological imprints of hidden dimensions continues with intensity. Each new observation of the cosmic microwave background, each survey of galaxies, each attempt to detect primordial gravitational waves is part of a larger effort to read the story of the early universe. Whether the evidence ultimately points to extra dimensions remains uncertain, but the pursuit itself is expanding our ability to measure and to imagine. In the final part of this chapter, we will explore how these cosmological ideas fit into the broader quest to understand the fate of the universe. If hidden dimensions shaped its beginning, might they also determine its end? The influence of hidden dimensions on the early universe opens naturally into questions about the far future. If extra dimensions shape the beginning, then they may also guide the fate of the cosmos. The geometry of unseen spaces is not static. Just as our familiar three dimensions of space expand with time, the curled or warped dimensions might evolve as well. Their dynamics could affect the acceleration of the universe, the balance of energy, and even the ultimate destiny of all matter. One possibility is that the compactified dimensions remain stable, locked into shapes determined at the dawn of time. In this case, their influence would be subtle but lasting. The values of fundamental constants, the strengths of forces, and the pattern of particle masses would remain fixed, set by the geometry of higher spaces. The universe would continue its expansion under the influence of dark energy, heading toward a cold and dilute future. Here, hidden dimensions would be silent architects, present in every interaction, but never changing after their formation. But stability is not guaranteed. In some models, the compactified dimensions can shift, tunneling from one configuration to another. If this were to happen, the constants of nature could change. Forces might strengthen or weaken, atoms might dissolve, and chemistry itself could be altered. Such a transition, if it occurred, would be catastrophic for any structures in the universe. Though unlikely on human timescales, over cosmic durations, the possibility cannot be ruled out. The fate of our universe may depend on the stability of spaces we cannot see. The expansion of the cosmos also raises questions about higher dimensions. The accelerated expansion observed today is often attributed to dark energy, but in some theories, it results from the influence of the bulk on our brain. Gravity leaking into higher dimensions could mimic the effects of a cosmological constant, pushing galaxies apart. If this is true, the ultimate fate of the universe may be tied not to a mysterious energy, but to the geometry of hidden spaces. Understanding whether the acceleration arises from dark energy or extra dimensions is one of the central challenges of modern cosmology. Brain cosmology also offers dramatic scenarios for the far future. If our universe is a three-brain drifting in a higher dimensional bulk, then it may one day collide with another brain. Such a collision could release energy on a cosmic scale, triggering conditions similar to the Big Bang. To inhabitants of our universe, it would appear as a sudden rebirth, a fiery beginning after eons of calm expansion. If the ekpyrotic or cyclic models are correct, such collisions may repeat endlessly, with each universe a chapter in an infinite series of brain interactions. Even the end of black holes may bear the imprint of extra dimensions. In higher dimensional theories, black holes can have different shapes and properties, from black strings to black brains. Their evaporation through Hawking radiation might proceed differently than in 4 dimensions. If microscopic black holes are ever detected, their behavior could reveal the structure of hidden dimensions and perhaps even provide clues about the long-term fate of massive black holes across the cosmos. For humanity, contemplating such scenarios is both humbling and inspiring. We live our lives on scales of years, centuries at most. The universe evolves over billions of years, shaped by forces and dimensions far beyond our perception. Hidden dimensions remind us that the cosmos is not only vast in space and time, but also in structure. What we see may be only the shadow of a deeper reality that governs both beginnings and endings. As this chapter closes, the story of hidden dimensions has carried us from the dawn of time to the distant future. They may have driven inflation, shaped the constants of nature, and influenced the expansion of the universe. They may still hold sway over its fate, guiding whether it expands forever, collapses, or cycles endlessly through brain collisions. The next chapter will turn directly to this question of destiny, exploring how a multidimensional universe might evolve in the farthest reaches of time. The fate of the universe has always been one of humanity's most profound questions. Once we learned that the cosmos had a beginning in the Big Bang, it was natural to wonder how it might end. Would it expand forever, freeze into silence, or collapse back into a fiery crunch? Hidden dimensions complicate this picture in extraordinary ways. They suggest that the destiny of all matter and energy may not be determined solely by the four dimensions we perceive, but also by the unseen geometry of higher spaces. In the simplest case, the extra dimensions are stable, frozen since the earliest moments of creation. Their compact geometry sets the constants of nature, the strengths of forces, the masses of particles, the very chemistry that makes life possible. If those shapes never change, then the universe follows the familiar path. Dark energy drives acceleration, galaxies drift farther apart, stars burn out, black holes evaporate, and a cold, dark future awaits. Hidden dimensions in this view are silent architects, having determined the rules but leaving the play to run its course. But stability is not guaranteed. Many higher dimensional models allow for metastability, where compactified spaces could tunnel into new shapes. If this were to happen, the constants of nature would suddenly shift. Gravity could strengthen or weaken, particles might lose their masses, and atoms could dissolve. To us, such a change would be instantaneous, a rewriting of physics itself. Though this is unlikely on human timescales, over cosmic durations, it cannot be dismissed. The future of everything may depend on the stability of dimensions we cannot see. Other possibilities emerge from brain cosmology. If our universe is a three-dimensional brain floating in a higher dimensional bulk, then it could collide with another brain. Such a collision would unleash a storm of energy, resembling a new Big Bang. The ekpyrotic and cyclic models propose that this process may have already happened before, that our Big Bang was simply one collision in an eternal cycle. In this view, the universe has no final end but endlessly repeats, with hidden dimensions orchestrating the rhythm of birth, death, and rebirth. Even the mysterious force of dark energy may be linked to higher dimensions. In standard cosmology, it is treated as a property of space-time itself. But in brain models, the observed acceleration may come from the way our brain interacts with the bulk. If so, the expansion we see today could change in the future, perhaps slowing or reversing. The ultimate fate of the cosmos may not be set in stone, but may depend on dynamics playing out in dimensions beyond perception. Black holes, too, reveal the influence of hidden dimensions. In more than 4 dimensions, their properties can differ dramatically. They may form as black strings or black brains, with stabilities unlike those in Einstein's relativity. Their evaporation could leak energy into the bulk as well as into our brain. If microscopic black holes ever appear in particle collisions, their behavior could offer clues to the ultimate destiny of massive black holes scattered across the universe. Taken together, these scenarios show that the fate of a multidimensional universe is far less certain than traditional pictures of heat, death, or collapse. Hidden dimensions open possibilities of cycles, phase transitions, rebirths, and transformations. They remind us that what feels like permanent reality may be only one configuration among many. The cosmos may not end, it may change, and in doing so, continue in ways we cannot yet foresee. To contemplate hidden dimensions is to confront the limits of human perception. For all of history, we have trusted our senses to define reality. But science has taught us that the visible world is only a fragment of existence. Atoms, fields, radiation, and dark matter, all invisible, are as real as the objects we touch. Extra dimensions extend this lesson to its most profound level. They tell us that even space itself may be larger, richer, and stranger than it appears. The challenge is not only scientific but philosophical. We cannot step into a 5th or 6th dimension. If they exist, They may be curled up smaller than an atom or warped into bulks far beyond our reach. Their presence can only be inferred through the weakness of gravity, the entropy of black holes, the patterns of cosmic radiation. To live with this idea is to accept that reality is not built for our senses, that nature is indifferent to what we can see. And yet, this realization is liberating. It shows that knowledge is not confined to perception. Mathematics and imagination, disciplined by evidence, extend our reach. Just as two-dimensional beings could never conceive of up and down without help, we extend our vision into hidden directions with equations, experiments, and thought. We may never walk through a Calabi-Yau manifold, but we can calculate its influence on particles and forces. In doing so, we learn that the boundaries of reality are wider than we once dreamed. This perspective reshapes our view of the universe itself. If we live on a brain, then our cosmos is not the whole of reality, but one slice in a larger structure. Other brains may exist, carrying other universes, perhaps with laws of physics unlike our own. We may never interact with them, yet the mere possibility transforms the meaning of the word universe. It becomes not all that exists, but simply all that we can observe. The idea also reshapes our view of ourselves. Humanity already seems small in a four-dimensional cosmos, a fragile species on a tiny planet, orbiting a modest star. In a multidimensional universe, we are smaller still, confined to a sliver of reality, and yet our minds can reach beyond. We are finite beings, but our thoughts extend into infinite structures. This tension between smallness and reach is what makes the pursuit of hidden dimensions so powerful. Certainty may never come. Evidence may remain indirect, woven into the weakness of gravity, the expansion of space, or the entropy of black holes. But science is not about absolute certainty. It is about building frameworks that explain, predict, and expand our understanding. Extra dimensions already serve this role. They unify theories, resolve paradoxes, and guide experiments. Whether or not they are ever confirmed directly, they have already changed the way we see reality. To live with the idea of hidden dimensions is to live with wonder. It is to accept that reality is inexhaustible, that knowledge is a journey without end. It is to see space and time not as the whole of existence, but as part of a larger fabric, and it is to recognize that the pursuit of understanding is itself a form of discovery, even when the answers remain hidden. The universe may conceal its higher dimensions forever, or it may reveal them in subtle signatures in the years ahead. Either way, their possibility expands the human spirit. It shows us that reality is richer than appearances, and that by seeking the unseen, we step closer to grasping the true depth of the cosmos.